neutrinos, etc. But these subatomic particles are formed by the combination of these three particles only. That's why these protons, electrons, neutrons are considered as fundamental particles. And you know very well, Nana, here it is, the signals are okay. And the protons, have positive 1 unit, and electrons have -1 unit, and the neutrons have, there is no charge for these particles. And if you see the charge, here it is plus 1.602 into 10 power minus 19 coulombs for the protons, and plus 4.8 into 10 power minus 10 ESU, electrostatic units. And coming to this electrons, the same charge but with opposite sign, that is minus 1.602 into 10 power minus 19 coulombs. Here it is minus 19 only here only the charge is different. And this is also minus 4.8 into 10 power minus 10 electrostatic units. Right? Here, if you see the weight or mass of this, here electrons have negligible weight when compared to the mass of the protons and neutrons. The protons have 1.672 into 10 power minus 27 kilograms, and the neutrons have 1.675 into 10 power minus 27 kilograms, whereas electrons have 9.11 into 10 power minus 31 kilograms. Right? These are about the such charges and masses. But here, regarding our topic, to know about the atomic structure, several scientists have tried their level best to put atomic models. Among them, J.J. Thompson proposed the atomic model with, he compared the atom with watermelon. In that, here, the red spongy matter is compared with the positive charge of the atom, and the seeds which are present is compared with the negative charge of the atom. But this model is unable to explain the spectrum, and hence Rutherford conducted alpha-ray scattering experiment that you have studied in already in your physics. And based upon that, he told that here the majority space of the atom is empty or hollow, and the entire mass and positive charge is situated at the center of the atom. And the atom is like this, and this center is called as nucleus. In the nucleus, what is the nucleus here? Here we have protons and neutrons. So the positive charge is due to presence of protons at the center, and in neutrons and protons, presence of protons and neutrons, which is responsible for the mass of the atom. And electrons are revolving around the nucleus, like planets are revolving around the sun. But according to classical mechanics, any object which is rotating should lose some energy, and at last it has to reach the nucleus. That is not happening. Why? Because if it loses, electrons come and join at the nucleus and the atom will be collapsed. If it is collapsed, there won't be any world. So for that, he explained that as electron is revolving around the nucleus in definite circular path, it experiences two types of forces. One is centripetal force. That means the force which is withdrawing the electron towards the nucleus. And another force which is pulling the electron away from the nucleus. This is called as centrifugal force. As both the forces are working on the electron in opposite direction with equal quantities, the electrons are moving like this. So it was a fundamental one, but it was also unable to explain what spectrum. So now we can see about the classical mechanics and what is the quantum mechanics. Now we can see. Here, classical mechanics. So the classical mechanics is the branch of physics which deals with the motion or movement of the object or of a body according to the Newton's laws of motion. And this deals with the macroscopic values. And if you see the quantum mechanics deals with the behavior of all the objects at the microscopic level. And at this level, the matter and energy are start to mathematically converge. They're going to mix because both can be observed to have wave-like behavior. Now we can see what are the failures of the classical theory. Or classical mechanics. According to classical mechanics, the emission of radiation is always discontinuous. Emission of radiation is discontinuous. And spectral distribution of energy are the relative tendencies of various radiations emitted by a black body. The spectral distribution is always by a black body. And the photoelectric emission of electron by metals on exposure to the UV light photoelectric emission of electrons by metals on exposure to the UV light. This is nothing but photoelectric effect. We can discuss in detail later. Third one, increase in the wavelength of light scattered by electrons. This is nothing but Compton effect. This also we can explain in detail later. Now we can see the comparison between classical mechanics and quantum mechanics. Here, as I told, the classical mechanics deals with the motion or movement of macroscopic, means large sized particles. Macroscopic or here, the quantum mechanics, as I told, it deals with the motion of microscopic bodies. So it deals with what? The motion of microscopic bodies, approximately the size of which is equal to atomic size or molecular size. Second one. Here, the state of the system is defined by the specification of positions and velocities of each particle of the system, along with how the particles are moving. The particles or the bodies or the objects can move from one place to one place by applying force on them. So by applying force on the object, what happens here? It can move. So such movement will be discussed clearly by the classical mechanics. And we know that specify the positions of the bodies and velocities of the bodies. And here, the state of system is completely defined and specified by knowing the wave function. The wave function is denoted by psi. So the wave function, which is associated with the motion of each particle of the system. Here, the position, velocities, etc., is explained by the force on acting them. And here, this is completely defined by knowing the wave function associated with the motion of each particle. Of the system. Third one. According to classical mechanics, any amount of energy may be emitted or absorbed by a body continuously. That means emission or absorption of energy by a body is continuous. But according to this one, energy is emitted or absorbed by a body only in discrete amount of packets. Here it is continuous according to classical mechanics. Here this is what? Discrete amount of energy packets. and always emission or absorption is discontinuous. The always emission and absorption of energy is discontinuous. And the minimum amount of energy emitted or absorbed by a body is called as quantum. What is quantum? The minimum amount of energy emitted or absorbed by a body is called quantum. So from this knowledge, what can we say here? The quantum is a packet of energy. Simply, what can we say? The quantum is a packet of energy. And there is a difference between quantum and photon. Photon also is a packet of energy, but when the quantum is, that means that when the energy is light energy, then that quantum is called as what? Photon. So this is nothing but what? Photon is also equal to quantum of energy, but that energy should be light energy only. But there is no condition, either it may be light energy or heat energy or electrical energy, etc., etc. And next one, here, as I told already, the classical mechanics is based on Newton's laws of motion. So therefore, this is also considered as Newtonian mechanics or Newtonian mechanics. Here it is based on completely probability. Concept. This is based on probability concept, which is on the basis of what? Heisenberg's uncertainty principle. And according to Heisenberg's uncertainty principle, probability, here the small particles with small mass, they show wave nature and particle nature. So this indicates what? Dual nature of the matter. This describes about the dual nature of the matter. So these are the some of the differences between classical mechanics and what? Quantum mechanics. Now we can enter an important aspect, that is black body radiation. So as we studied already in intermediate education, and you have studied in your first year BSc, here any object which absorbs entire incident light energy or entire radiations which is incident on that is called as a black body. So the object which absorbs all radiation which is incident on it, and also it is a perfect emitter also. So therefore, a perfect black body absorbs 100% radiations which are incident on it. And also it emits 100% emission takes place. Generally, here if you see this, the block body will be like this generally. A small projection will be there, this one. As a light ray enters here, here this reflects for several times. This reflects 100% radiation on it and emits. Generally, this is designed by a scientist called Ferri. Therefore, it is also called as Ferri's black body. And here it consists of hollow, double-walled one. Here, this is coated with black color. Here, when any radiations enter the sphere through the opening, so what happens here? It suffers multiple reflections at this inner walls. So what happens here? Initially, by so many times reflection taking place, and hence 97% reflections have been absorbed. And again, after some more reflections, almost entire radiation is absorbed. So what is the role of this projection? Projection helps to avoid any direct reflection. So generally, here, what is the role of projection? It avoids any direct reflection when this block body is placed both at fixed temperature and heat radiations comes out of the hole. So when, for example, 100% absorption and 100% emission takes place, this perfect black body is also called as full radiations. The radiations which are emitted by a block body is called as what? Full radiations or total radiations. So here, so because the hole is there, from that one only, here what is happening? The reflections are taking place, the light is coming. Therefore, the opening acts as, this opening acts as black body radiator. So always remember, always, because this is the black body radiator, what can we say here? The opening only. The opening only acts as black body. And the walls cannot be considered as black body. The walls cannot act as, the walls cannot act as black body. So always remember the wavelength of radiations emitted by a block body or a hot body is inversely proportional to the temperature. So the lambda is inversely proportional to temperature. The emission, this is. And as we know, C is equals to nu lambda. C is equal to nu lambda. So therefore, nu is directly proportional to absolute temperature, frequency. Therefore, frequency of our radiations emitted by a hot body or black body is directly proportional to the temperature. And for example, if you see the radiations, if you see the plot of this one, energy density and wavelength, we can see the plot. This is wavelength of the instant radiation. Energy density. So by observing these plots, we can conclude that for each temperature, there is a particular wavelength at which energy radiated is maximum. At this temperature, this is the radiation is maximum, and here for this one, this is radiation is maximum, and here it's for this. With the increase in temperature, the position of the maximum shifts towards lower wavelength. With the increasing temperature, the position of the maximum becomes more noticeable. And we can see the failures of wave theory to explain the black body radiation. Here, wave theory cannot explain the color change. The wave theory cannot explain the color change. Why? Because the radiation of only one wavelength could be possibly emitted by a black body, irrespective of its temperature. And there should be only one color, according to wave theory. But we can explain with quantum mechanics. Of black body radiation. By quantum theory or quantum mechanics. Here, as frequency emitted by a hot body or black body, as we told, the nu is directly proportional to temperature. So when temperature is of a body is low, when temperature of a body is low, it will emit low frequency. That is, or longer wavelength. When low frequency is nothing but what? Longer wavelength. So therefore, at low temperature, the low radiations, that means the frequency of the radiations is low. So therefore, the radiations will fall in red color region. As the temperature increases, that is at high temperature, what happens? It emits high frequency radiations. The radiations will have high frequency. When the radiations are high frequency, automatically the wavelength will be lower. So automatically at this high frequency, the radiations will fall in the yellow region. The radiations will be in the yellow region. At further high temperatures, here what happens automatically, the radiations of, that means the emitted radiations will be further more high frequency. So at this time, what happens here, automatically the radiations will fall in the UV region. At low temperatures, the radiation will fall in red region. At high temperatures, they can fall in yellow region. At further high temperatures, the radiations will fall in the UV region, and hence the body looks white. So therefore, the quantum theory explains why the color of black body changes from red to white, red to yellow, and yellow to white. This was not explained by the classical theory. And another one, heat capacities of solids. First, we should know what is heat capacity. Heat capacity is nothing but the amount of heat energy required to increase the temperature of an object by 1 degree centigrade. The amount of heat energy required to increase the temperature of an object by 1 degree centigrade is called as heat capacity. The units are joule per Kelvin. And if you want specific heat capacity, this specific heat capacity is found by the dividing this heat capacity by its mass. For example, if you want molar heat capacity, then we have to divide it by mole, amount of mass in moles. Now we can see about this one. According to Dulong-Petit law, the gram heat capacity of an element is constant. According to Dulong-Petit's law, the gram heat capacity, this is nothing but what? The product of specific heat and atomic mass. The gram heat capacity is nothing but what? Here, specific heat and atomic mass. So the gram heat capacity of an object or of an element is constant. So means what here? This is the gram heat capacity is constant for all solid elements. So therefore, for all the solid elements, the heat capacity is constant, and that is approximately equal to 6 calories per gram atom. So how can we say this here? Specific heat, which is multiplied by atomic mass. This is nothing but what? Gram heat capacity. Specific heat to atomic mass will give us what? Gram heat capacity. This is equals to what? 6 calories gram atom inverse. And next one is Rayleigh-Jean's law. Here, the Rayleigh-Jean's law describes the spectral radiance of the electromagnetic radiation. What does it explain? It describes spectral radiance of electromagnetic radiation. At all wavelengths. Of what? From a black body at a given temperature through classical arguments. So therefore, for wavelength, this is given by B lambda at temperature, that is absolute temperature, is given by an equation 2C KB into T by lambda to the power 4. For example, if the frequency is given, B nu at temperature T is given by 2 nu square KB T by C to the power 4. As I told, C is equals to nu lambda. So here, what is this here? C is equals to velocity of the light, or speed of the light. And KB is called as Boltzmann constant. The value is 1.38 into 10 power minus 16 erg per Kelvin. Or if you want to mention in the joules, 1.38 into 10 power minus 23 joule per Kelvin. So here, the Rayleigh-Jean's law agrees with the experimental results at large wavelengths. And at shorter wavelength, it is strongly disagrees. Why? What is the reason? This inconsistency between the observations and the predictions of classical physics is commonly known as UV catastrophe. And this led to the foundation of quantum mechanics in the early 20th century. So based on this, we can see about we are entering to the quantum mechanics, that is Planck's quantum theory. Planck's quantum theory. According to Planck's quantum theory, as already I told in the classical, in the difference between classical mechanics and what this one, quantum mechanics, there I told. Here the energy absorbed or emitted by a body discontinuously in the form of small packets. So here the energy packets so the emission or absorption is taken place by the bodies discontinuously in the form of energy packets. And each pocket of energy, already we discussed this, each pocket of energy, each packet of energy is called quantum. For example, if the energy is light energy, in the case of light, energy, what happens here? The quantum becomes photon. And the energy of each photon is dependent on the frequency of radiation, that is given by E is equals to h nu. The energy of each photon is given by E is equal to h nu, where h is Planck's constant. Where h is Planck's constant, the value is given by 6.625 into 10 power minus 27 nana erg second. Nana, don't confuse that. This is not erg per second. This is erg second. So sometimes this is also given in the form of multiple choice questions. So one of the values is given as erg per second, but it is very tough to remember. No, sorry, not. We should be very tough not to commit the mistake. We should be very strong enough. We should write only erg second, not erg per second. And this can also be written as 6.625 into 10 power minus 34 joule second. And here, if you want to mention in kilojoules, this becomes 3.99 into 10 power minus 13 kilojoules second per mole. Here, the fourth point is when a body can absorb or emit only one photon or some whole number multiple of it. So as I told, E is equals to h nu. So this can also be written as E is equal to nh nu, where n is equal to 1, 2, 3, 4, and so on. But not n is not equal to 1.2 or 2.3 and so on. No fractions will be there. Only whole multiple of that one. These are the important aspects of Planck's quantum theory. It is very, very important. Based on that, we can discuss some problems. So Einstein utilized this quantum theory to explain the photoelectric effect. So the incident photon transfers its total energy to the electrons which are present on the surface of the metal. So by absorbing the energy, so what happens? The electrons are very active and they can escape from the metal surface. This is nothing but this is called as what? Photoelectric effect. And here, the escaping electrons have some kinetic energy. And this is energy is equal to the instant energy of the incident photon and minus energy of the required to escape from the metal surface. That is given by when kinetic energy is equals to half mv square. This is given by h nu minus E1, where E1 is equals to h nu naught. So this is called as work function. What is this nu naught? This is a threshold frequency. Here, if the energy of incident photon is greater than E1, then photoelectrons will be emitted.
डॉक्टर
So,
साहब
sir.
कब तक कंटिन्यू करते हैं?
So, shall I stop or shall I continue? 5 to 10 minutes?
నన్ను కంటిన్యూషన్ లో ఉంటే కంప్లీట్ చేసి క్లోజ్ చేయండి.
ఒక 5 to 10 minutes అన్న.
రైట్ డన్.
ఈ టాపిక్ ఆన్ చేసి. Thank you డాక్టర్ సాబ్. So here, if the energy of instant photon is greater than E1, then photoelectrons will be emitted. So as the intensity of the light increased, automatically the number of photons increases. So therefore, the number of photoelectrons also increases. If the instant photon has less energy, automatically the photoelectrons will not be emitted to the maximum extent. So that particular optimum energy required to eject the photoelectrons is called as what? Threshold frequency or critical frequency. So beyond that, they are capable of ejection of the electrons, but some optimum frequency is required to eject the electrons. That is called as what? Threshold frequency. If the instant photon has frequency more than critical frequency, so automatically the excess energy of photon gets transferred to the ejected electrons as their kinetic energy. So the fact is that the light energy which is propagated in terms of photons or quanta says that light should have a particle nature. But at the same time, light has exhibiting two properties like interference and diffraction. This indicates the wave nature of the light. And hence, what can we say? The light has dual nature, that is particle nature and what? Wave nature. If you see the photoelectric effect perfectly, when an electromagnetic radiation of critical or threshold frequency falls upon the surface of a metal, so what I told just now, optimum frequency is required. That frequency is called as what? Threshold frequency or critical frequency. So by sending such frequency on the surface of the metals, they can eject the electrons. So what happens by the ejection of electrons, the surface of the metal will get the positive charge because all the electrons are left. And this is called as what? Photoelectric effect. The production of electrons from metal surfaces by the action of light is explained with the help of photoelectric cell. So this is like this. So the photoelectric cell is a sensitive device for the detection of the light radiations. It consists of evacuated globe or tube. It contains a platform P coated with the thin film like potassium or cesium. And a wire is placed above the platform P. And the circuit is completed through galvanometer G and a battery. Now, for example, if you draw like this, this is the incident light on the metal surface. This is vacuum. This is the wire. This is the platform. Here, this is coated with cesium or potassium. And this is connected to galvanometer. And battery. By this, the circuit is completed. So when light of suitable frequency falls on the platform P, the electrons are ejected. So these move towards the wire neck and the current flows through the circuit, which is indicated by the galvanometer. So when light of critical or threshold frequency falls on the metal, it provides a different amount of energy to overcome the attraction forces of the nucleus or the electrons. By that, the electrons are ejected. So this is some of the things about the photoelectric effect. We can stop here, and the rest of the thing will be discussed in the next class. Now I am hand over to Dr. Ramesh, who is recently awarded as best teacher. Really, we are proud of him. The dedication. So many students from poor background are getting seats in wonderful universities and even central universities. So thank you, Dr. Ramesh. Sir, I will stop here. Dr. Ramesh Garu.
Thank you.